With today's lecture, I'd like to start back with this epiphyseal plate. As I told you in the previous lecture, I really have a fascination with the epiphyseal plates and the epiphyseal lines. One of the things I like to talk about at this point is sometimes we have children, all right, we know of children that are extremely vertically challenged, shall we say, and we take them to the doctor and we want maybe some hormone replacement, or we want some growth hormones, or something prescribed to make this not an issue, quote unquote, not an issue. One of the first things the doctor's going to do is do an x-ray of one of the long bones or a couple of the long bones to see if the epiphyseal plate is in place. Because as we said in the previous lecture, as long as the epiphyseal plate, that gap as we see in these x-rays, is present, we have the individual has the ability to grow. However, if in fact when the doctor looks at the x-ray and sees the epiphyseal line, sees that ossification, sees that it's been converted to bone, there's really nothing that can be done short of really, really drastic surgical interventions. Once it's been ossified, once it's turned to bone, the epiphyseal plate no longer has the ability to allow for growth. So I just wanted to touch on that because I find it really interesting. Next, we look at our membranes. These are going to be membranous tissue that surrounds the bone itself. We're going to start on with the superficial most layer, and that's going to be the periosteum. It is a double-layered membrane, which means it's going to be made up of two membranes. The outermost layer is referred to as the fibrous layer. It's going to be made up of dense, irregular connective tissue. Now again, I'm going to ask you to recall our first lab when we were looking at our tissue and what dense, regular connective tissue looked like. And what you're going to hopefully remember is all of the fibers went in one direction, which makes that tissue very, very, very strong in that one direction. The problem is if there's an impact in the opposite direction, perpendicular to those lines, it's very, very fragile and it will be damaged very easily. The periosteum, the fibrous layer of the periosteum, is made of dense, irregular connective tissues. If you look in your textbook as to what that's going to look like, it's going to be fibrous, as the name would make you think, but those fibers go at all different angles, so it increases the strength from any angle of that tissue might be impacted, so it makes it a stronger overall tissue. Now, the inner layer is called the osteogenic layer. Osteo is going to be bone, and the root gen from Genesis, the Bible story, right, is going to be to make. So the osteogenic layer is going to be in charge of making of the bone matrix. Here we're going to find primarily cells that are called osteoblasts. Osteoblasts are cells that are in charge of making the bony matrix. So it would make sense that if I'm going to have this osteogenic layer, which is there to make bone, that these osteoblasts would be present because they are in charge of making that bony matrix. The periosteum is richly supplied by nerves, blood vessels, and lymph vessels. As we see in lab, bones often just kind of look like sticks. They're inert. They look like they've never been alive, but they are in fact living tissue that has quite a lot of blood supplied to them, many, many living cells, nerves, lymph vessels, the whole shoot and match. That's how we know if you've really broken a bone badly that there is a lot of bleeding, because the blood vessels in that bone, when it breaks, are going to be damaged. We also have an endosteum. Endo means within. So the endosteum is going to be found lining internal spaces. Well, what internal spaces do we find in a long bone? Because again, remember, we're talking about the long bone. We're going to find the endosteum lining the medullary cavities, that space where we find our yellow marrow in the diaphysis of our long bones, and the spaces within the spongy bone. Spongy bone is what makes up our ends, our epiphyses of our long bones. In this area within the endosteum, we're going to find osteoblasts and osteoclasts. Osteoblasts are those cells that are going to make the bony matrix, and osteoclasts are cells that are going to break down the bony matrix. In a little bit, we have a slide that talks about these suffixes, so don't get too crazy right now. We'll review those in a moment. We look at our diagram here, and you'll see that the periosteum is pulled away towards the middle of the diaphysis, the middle of the shaft on the left side, and you can see blood vessels. Those red lines are representing the blood vessels. The periosteum is highly vascularized because we have to get the blood vessels into the bone itself so that we can nourish all of the many cells that are going to be contained there. Now, the microscopic anatomy. We're done with our gross anatomy. Now we're on microscopic anatomy. And I'm going to ask that you really concentrate. Think about what our bone looked like on the slides in lab. This is the one that I think looks like a tree trunk, right? That had rings that would make you think of a tree trunk. The structural unit of compact bone is called an osteon or a Haversian system. Again, we'll say this often in coming weeks. Oftentimes, if an individual, a scientist, discovers something, they get to name it after themselves. Haversian system, my guess, was discovered by a Dr. Havers and said, hey, I'm going to name it after me. What we're trying to do is move away from those, what we refer to as historic names, and get more anatomical. That's why we're moving towards the osteon. But these two names, osteon and Haversian system, are interchangeable with one another. The osteon is going to be one tree trunk, one target, if you will. If you think of a dartboard, right, that's going to be one osteon or one Haversian system. Each osteon is made up of several pieces. First, we'll talk about the lamillae. Right? We have an E, so we're talking about multiple lamella. Okay, so lamillae is the plural for the word. These are concentric rings of hard bone matrix around a central canal. Again, think of what you saw on your slide in lab. There was a black circle in the middle. That's going to be the central canal. And then the white rings around it are those concentric rings that we're speaking of. Each osteon is made up of, contains between 4 and 20 layers or rings, 4 or 20 lamillae, if you will. So what this diagram is showing you, popped up, is one osteon, and each of those rings represent a lamella. You'll notice in the center there's a red and a blue vessel. That's an artery and a vein that's filling the central canal. That central canal is often referred to as the Haversian canal. It is oriented along the long axis, so it's going to go lengthwise along the bone from, say, the proximal to the distal end. Typically, we're going to find blood vessels and nerves contained within them. If you look closely at the center of each of those osteon, you're going to see a red, a blue, and a yellow speck. The red is the artery, the blue is the vein, and the yellow is representing the nerve. We have to get those vessels as a nerve deep into the bone so that we can take care of and maintain all of the cells that we're going to find within the bony tissue. You'll notice that we have something peeled away. That's the periosteum. And those vessels are coming from the periosteum, penetrating into the bony matrix. The Haversian canal is another spot where we're going to find it being lined by the endosteum that we spoke of earlier. Next, we have the Volkmann's canal. Volkmann's canal run perpendicular to the Haversian canals. So we have the Haversian canals going lengthwise along the long axis of the bone. We have to connect them. We have to have a way for those blood vessels to get from one, Haversian canal to the next. That's where our Volkmann's canals come in. On your diagram here on the slide, they're referred to as perforating canals. See, even now I can't speak. They're going to allow the blood vessels and nerves to get deeper into the bony tissue. And as we say, it's going to connect the Haversian canals, the medullary cavity to the periosteum. And if you follow it, you're going to see that you have a pathway to get between central canals or the Haversian canals and the outer surface and the inner surface of the cell using those perforating or Volkmann's canals as well. This is what we're talking about, folks. This is what you saw on your slides. You're seeing a bullseye, right? The dark black circle at the center, that's going to be the Haversian canal. The white circles are those lamellae that we spoke of. Next, please notice, because we're going to talk about the osteocytes in a second. Those are going to be the bone cells. Those are those black, kind of ovally shaped looking guys that we see sandwiched between the lamella. Now, this is a good diagram. This is from your textbook. The cell proper is that oval shaped, and that's that dark part you saw. Those finger-like projections are going to be really, really important. We're going to talk about those in a sec, but please keep in mind that that's what the osteocyte is going to look like. You have a centralized portion of the cell, and you have these long projections sticking off of the cell body. Next, we have an osteocyte. That's our mature spider-shaped bone cells. That's the diagram we saw earlier, right? And it's spider-shaped, way, way more legs than a spider would have, but we have the central body, we have those projections sticking off of it. Osteocytes are responsible for bone matrix maintenance. We had cells, the osteoblasts, that make the bone matrix. We have osteoclasts that break it down. The osteocyte just kind of keeps the status quo, right? Make sure that everything is running and it's staying in good working order. Our osteocytes are found within lacunae. Again, we've got an E at the end, so that's going to be plural. If you look at the bottom part of that diagram, the lacuna is a space, a physical space, and that's what you see when you look at your cells, those black kind of squished oval parts between the lamella. That is the lacuna because the cells are long gone. That's dead tissue. The cells are long gone, but that's the space because the bony matrix is hard like a rock. So the cells have to have a space to live in, and that's where the lacuna come into play. Next, we have the canaliculi. I always think it sounds like an Italian dish. Oh, I'd like a nice Chianti to go with my canaliculi. But a canaliculi are hair-like canals because, again, if we think about the shape of the living cell, it's spider-shaped. We have the centralized cell body with our finger-like projections. If the bone matrix is hard, we have to have space. We have to have a tunnel for those fingers to be in, and that's what a canaliculus is going to be. It connects the projections of adjacent osteocytes. So these tunnels where the finger-like projections, it allows one cell to communicate to be in close proximity to another. This is going to allow for diffusion between the cells because if you look at the top diagram, some cells are going to be in quite close proximity to the blood vessels and the nerves. I have to have a way to get the materials, the oxygen, nutrients from those blood vessels to the cells further away from it. The projections from the cells allow that to happen. The canaliculi give us a space for those projections to reside. Now, I keep talking about this bone matrix, the hard bone matrix. What the heck is it? It's not a cellular bit. It's not alive. This is the material between the cells. This is the material that is made and maintained by these various osteotypes of cells. It is a very specific combination of organic and inorganic elements that makes a bone act and work like a bone should. Okay, it's produced by the cells, but it does not have cells in it. So first we'll talk about the organic component. Approximately 35% of the bone matrix is organic. We refer to it as the osteoid. One of the main components of that osteoid is collagen. Collagen is present to allow for bone flexibility and something called tensile strength. We typically don't think of a bone as being necessarily flexible, but if you've ever closed your fingers in a car door, okay, they are a certain bending. Your bone doesn't shatter because it's been closed in the car door.